Now we are going to discuss the physical properties and chemical properties of aldehydes and ketones. First we will go for physical properties. Physical properties of carbonyl compounds. In this first we will discuss about physical state. Physical state of carbonyl compounds. When come to the physical state of carbonyl compounds, the first compound of aldehyde is formaldehyde, that is HCHO, formaldehyde, and this formaldehyde is a gas at room temperature RT. Whereas CH3CHO acetaldehyde is a liquid, and higher aldehydes ketones may be liquids or solids. Now the next one is very important, that is boiling point. When come to the boiling point of aldehydes and ketones, the boiling point of aldehydes, I mean carbonyl compounds, is more than the boiling point of hydrocarbons. Hydrocarbons means alkanes, alkynes. Here, because in carbonyl compounds, the molecules are held by DD forces. Dipole forces are present in carbonyl compounds. Due to presence of dipole interaction between the aldehydes or ketone molecules, they are having a more boiling point than hydrocarbons. In hydrocarbons, the force of interaction between the molecules is van der Waals force. Van der Waals forces. They are held by weak van der Waals forces, but they are held, and whereas carbonyl compounds are held by little stronger dipole interactions. So because of this dipole interactions, the boiling point of carbonyl compounds is more than the boiling point of hydrocarbons. Now, but the boiling point of carbonyl compounds, is less than the boiling point of carboxylic acids and alcohols. The reason for this is you know that carboxylic acids and alcohols contain a hydrogen bond. Due to presence of hydrogen bond in carboxylic acids and alcohols, the boiling point of carbonyl compounds is less than the boiling point of carboxylic acids and alcohols. Now, if you compare aldehydes and ketones, among aldehydes and ketones, the boiling point is more for ketones. The boiling point of ketones is more than the boiling point of aldehydes. Okay. Now we will go for solubility. Solubility of aldehydes and ketones. If you take lower aldehydes or ketones, lower carbonyl compounds, they are soluble in water. This is due to formation of hydrogen bonds. So lower aldehydes and ketones can form hydrogen bonds with water. So due to the formation of hydrogen bonds with water, they are soluble in water. But as number of carbon atoms increases, you know, the hydrophobic nature of alkyl group increases. So the solubility gradually decreases. It means lower aldehydes and ketones are soluble in water, but whereas higher aldehydes and ketones are insoluble in water. And when come to this other solvent like organic solvents, these carbonyl compounds are soluble in organic solvents like benzene, toluene, next CCl4. Okay. Carbonyl compounds are soluble in organic solvents. They are called as non-polar solvent, that you know very well. Okay. Now we will go for order of aldehydes and ketones. You know, lower aldehydes are having a pungent smell. They are having a bad odor, pungent smell. And in aldehydes, as number of carbon atoms increase, the pungent nature gradually decreases, whereas the fragrance gradually increases. You know that benzaldehyde, okay, is used as almond flavor. Okay, flavor, it is used as almond flavor. So, I mean aldehydes can be used as flavoring agents for their fragrance. Okay, in aldehydes, as number of carbon atoms increase, their fragrance gradually increase and pungent nature gradually decreases. So, these are the physical properties of aldehydes and ketones. The next one is nature, structure of carbonyl carbon. First, we will go for structure of carbonyl carbon. You know that C double bond O is called as carbonyl carbon, and in this carbon is bonded by double bond. So, the hybridization of this carbonyl carbon is sp2, and you know the shape is trigonal planar, and the bond angle is 120 degrees. And this carbonyl carbon is bonded by, you know, this is bonded by a sigma bond, sigma bond, sigma bond. So, 3 sigma bonds and 1 pi bond. And the type of overlapping involved, okay, between the formation of sigma bond between carbon and oxygen is sigma sp to p. This is the type of overlapping involved in the formation of sigma bond between carbon and oxygen, and 1 pi bond is there. You know that double bond consists of 1 sigma and 1 pi bond. So, this is the structure of a carbonyl carbon. Now, the next one, we will go for its nature. Okay, this is about the structure, and we will go for its nature. When come to the nature, you know that among carbon and oxygen is more electronegative. Because of more electronegativity, it will take this pi electrons, and it gets a negative charge and it gets a positive charge. Okay, due to the presence of positive charge on this carbonyl carbon can function as what? Electrophile. So, because of positive charge, the carbonyl carbon behave as electrophile, and it will have a greater tendency of attracting a nucleophile. Okay, so therefore, this about the nature and structure of carbonyl carbon. Now, we will go for reactivity of carbonyl carbon, or reactivity of aldehydes and ketones. When come to the reactivity of carbonyl carbon depends on 2 factors in this. Okay. So, the reactivity of carbonyl carbon is influenced by electronic factor and steric factor. What does it mean? What is electronic factor and what is steric factor? How they influence the reactivity of aldehydes and ketones. Okay. Now, first we will go for electronic factor. Just now I said that carbonyl carbon is having a positive charge. So, if the magnitude of positive charge is more on this carbonyl carbon, it means if electronic factor is more, if the magnitude of positive charge on the carbonyl carbon is more, then it will have more reactivity. So, therefore, to have more reactivity, the magnitude of positive charge on the carbonyl carbon should be more. If electronic factor is more, reactivity is more. And now we will go for a steric factor. When come to the steric factor, it indicates the crowdiness of alkyl groups around this carbonyl carbon. If crowding around this carbonyl carbon increases, the reactivity, the reactivity gradually decreases. So, therefore, among this electronic factor and steric factor, electronic factor is increasing the reactivity of carbonyl compounds, but whereas steric factor is decreasing the reactivity of carbonyl carbon or carbonyl compounds. So, therefore, if you take aldehydes and ketones, now first I am taking aldehydes, or C double bond OH. You know that in aldehydes, the carbonyl carbon is bonded with the hydrogen and alkyl group. Okay, and you know that alkyl groups will have a plus I effect. Okay, they decreases the positive charge on the carbonyl carbon. So, because of this, they are less. They are more reactive towards nucleophilic addition reactions when compared to the ketones. Now, I am taking ketones, or C double bond OR. You see here, in this case electronic factor is more because only one alkyl group is there, Okay, but when come to the ketones, two alkyl groups are there and they decreases the positive magnitude of positive charge on the carbonyl carbon. So therefore, that they decrease the reactivity. So therefore, by considering electronic factor and steric factor, here there is a steric factor in ketones. There is a steric hindrance. Crowding is more around the carbonyl carbon in the ketones. Because of this, ketones are less reactive than aldehydes. If you take order of reactivity, aldehydes are more reactive than ketones. So the most reactive carbonyl compound is a formaldehyde. This is the most reactive carbonyl compound. Next one is aldehydes, RCHO. So among the carbonyl compounds, the most reactive carbonyl compound is formaldehyde. Why? Because in formaldehyde, electronic factor is more on this, magnitude of positive charge is more on the carbonyl carbon, and steric crowding is very less. You know that if the electronic factor is more and steric hindrance is less, then that carbonyl compound will have more reactivity. So in formaldehyde, the magnitude of positive charge, electronic factor is more and steric hindrance is less. Because of this, formaldehyde is most reactive carbonyl compound, and the least reactive is diphenyl ketone is the least reactive, and you have to remember this order. This is very important. So therefore, if you analyze all these things, aldehydes are more reactive than ketones. Among the aldehydes, aliphatic aldehydes are more reactive than aromatic aldehydes. So I mean formaldehyde is more reactive than aliphatic aldehydes, and aliphatic aldehydes are more reactive than benzoaldehyde, aromatic aldehydes. Carbonyl compounds. You know that in carbonyl carbon, carbon is having a positive charge and oxygen is having negative charge. Due to the presence of positive charge on the carbon, it will have a tendency of attracting a nucleophile. So therefore, carbonyl compounds undergo nucleophilic addition reactions. Nucleophilic addition reactions are nothing but the reactions in which a nucleophile is added to the multiple bonded atoms. Are called as what? Nucleophilic addition reaction. So carbonyl compounds, aldehydes and ketones majorly undergo nucleophilic addition reactions. Now if this nucleophilic addition reaction takes place in the presence of a strong nucleophile, if nucleophile is strong, then you know that carbonyl carbon is having a trigonal planar shape, C double bond O, this is A, this is a B, and this is having a trigonal planar shape. And if the nucleophile is a strong, Nu minus, then directly this nucleophile will attack on the carbon and will get B, and you will get a nucleophile, and this one further reacts with H plus, you will get C. So here the shape of this carbon is a trigonal planar, and but here the product is having a tetrahedral. So if the nucleophile is strong, then this reaction takes place. And the second case, if nucleophile is weak, say the nucleophile is weak, in this case the reaction will take place like this. Now C, A, P and double bond O. In this case H plus, and this takes place in the presence of acid catalyzer. So H plus will interact with this oxygen and forms oxonium ion, double bond O. This is called as oxonium ion, and this oxonium ion is highly reactive because this will be taken by this oxygen, and when nucleophile, I said this is a weak nucleophile, so therefore this weak nucleophile will attack on carbon, and finally you will get nucleophile. So, if it is a strong nucleophile, then directly the nucleophile will attack on this carbon, but if it is a weak nucleophile, first proton H plus will attack on the oxygen and forms a oxonium ion, and that oxonium ion is highly reactive towards this nucleophile, and finally you will get this product. Now we will take various examples for nucleophilic addition reactions. Addition with HCN, hydrogen cyanide. Carbonyl, I am writing like this, C double bond O, it is H. Okay, here you can write RH. Whenever aldehydes or ketones react with HCN, you will get a cyanohydrin. We will take aldehydes R, C double bond O, H. When react with HCN, and this reaction takes place in the presence of a base and pH around 9 to 10. Okay, in this case, you know that H is having a positive charge and cyanide is having a negative charge, and here you have to add this cyanide to the carbon and hydrogen to the oxygen. So, finally you will get RCOH and H, this is N. This is called as what? Cyanohydrin. Now, similarly you can take ketones R, C double bond O, R. When react with HCN in the presence of base, you will get R, C, OH, R, and you will get CN. Okay. So, in this the species which is attacking on the carbon is cyanide, and this is what? Nucleophile. So, nucleophile is added first to this carbon, that is why this reaction is called as what? Nucleophilic addition reactions. When aldehydes or ketones react with HCN, you will get a cyanohydrin. Now, we will take one example, acetaldehyde, CH3CHO, or else you can write C double bond OH. When react with HCN, then here what you will get? You will get CH3COH, H and CN. This is called as what? Acetaldehyde cyanohydrin. If you take acetone, CH3C double bond O, CH3, when react with HCN, okay. Now here you will get CH3C OH, CH3, and this is CN. It is known as what? Acetone cyanohydrin. Okay. Now we will go for the second reaction. Reaction with or addition with sodium bisulfate, NaHCO3, and these reactions are reversible reactions. Okay. Now reaction with sodium bisulfate. When aldehydes or ketones, okay, when aldehydes or ketones R, C double bond O, H, when they react with sodium bisulfate, reversible reaction, you will get R, C, SO3, H, and it is what? OH. Now this again react with R, C double, okay, C, SO3H, and it becomes what? O, Na, like this. And here you will get a white, this is what? White crystalline solid. And you will get when aldehydes or ketones react with sodium bisulfite, you will get a white crystalline precipitate, and that on reaction with water, this further react with water, will get a aldehyde or ketone. Now I am taking a ketone R, C double bond O, R. When it react with sodium bisulfite, here you will get R, C, OH, R, SO3, Na. Okay. Now, so this is called as what? Sodium sulfite salt, and this is white crystalline solid. White crystalline solid. And when it react with water, okay, again you will get R, C double bond O, R. So therefore, the sodium bisulfate can be used for the separation and purification of aldehydes and ketones. Okay. Now next, third reaction is reaction with alcohols. Aldehydes and ketones can also react with alcohols in the presence of HCl and forms amiacetols and acetols. Now I am taking aldehydes first. Aldehydes react with the alcohols in the presence of dry HCl, and you will get R, C, OH, H and O, R. This is called what? Hemiacetal. This hemiacetal again react with alcohol in the presence of dry HCl, and again you will get R, C, OR dash, H, OR dash. This is called what? Acetal. Okay. So, aldehydes react with alcohols in the presence of dry HCl and forms hemiacetal, and that further react with alcohol and forms acetol. Now, if you take a ketone, R, C double bond O, R. Now, here I am taking a ethylene glycol, OH, OH. It is called as ethylene glycol. So, here you will get a cyclic ketols, O, CH2, CH2. This is called as cyclic ketol. Cyclic ketols. Now, this is ethylene glycol, and the cyclic ketols on hydrolysis, again you will get R, C, R double bond O, ketones will get. Reaction with PCl5. Aldehydes and ketones react with PCl5. C double bond O, R, H, R. It may be aldehyde or ketone. React with PCl5, and here you will get C, R, H or R, Cl, Cl plus PO, Cl3. Here you will get gem dihalides, geminal dihalides. Geminal dihalides. We will take one example. Say I have taken CH3, C double bond O, CH3 acetone. When acetone react with the PCl5, here you will get CH3, C, Cl, Cl, and this is CH3. Okay, this is called what? Isopropylidine chloride, or else you can write 2,2 dichloropropane. Okay, it is a gem dihalide. You know, dihalides are of two types. They are vicinal dihalides and geminal dihalides. If halogens are present on the adjacent carbons, then they are called as vicinal dihalides, and if halogens are present on the same carbon, they are called as geminal dihalides. So, when aldehydes or ketones react with PCl5, they form geminal dihalides. Now, the next one is reaction with RMGX, Grignard reagent. RMGX is called as a Grignard reagent. So, you know that when aldehydes react with, when formaldehyde, I am taking formaldehyde, when formaldehyde react with a Grignard reagent RMGX, in this case you will get RCH2OH, will get primary alcohols. This you already discussed in alcohol chapter. So, when formaldehyde react with the Grignard reagent, we will get primary alcohols. And similarly, other than formaldehyde, if you take aldehyde other than formaldehyde, aldehydes on reaction with RMGX, okay, gives secondary alcohols. Now, we will take one example. Say I have taken acetaldehyde. When acetaldehyde react with CH3 MgCl, this is known as methyl magnesium chloride. When it react with the methyl magnesium chloride followed by hydrolysis, here you will get CH3, CH, OH, and this is CH3. Isopropyl alcohol you will get. It is a secondary alcohol. And if you take ketone, ketones are reaction with RMGX followed by hydrolysis, you will get tertiary alcohols. Okay. Now, acetone CH3 C double bond O CH3. When acetone react with CH3 MgBr, methyl magnesium bromide, here you will get CH3 C OH, CH3 and CH3. This is called what? Tertiary butyl alcohol. It is a tertiary alcohol. So, therefore, Formaldehyde on reaction with the Grignard reagent will get primary alcohols. Aldehydes on reaction with the Grignard reagent will get secondary alcohols, and ketones on reaction with Grignard reagent will get tertiary alcohols. We will go for the reactions. Okay, reactions of aldehydes and ketones with ammonia derivatives. So first of all, we discuss what are those derivatives. You know that NH3 is nothing but ammonia, and RNH2 are called as primary amines. Okay, and whereas NH2 is called as what? Hydrazine or hydrazine. Okay, and next NH2OH is called as hydroxyl amine. Okay, hydroxyl amine, and PH NH2, this is called what? Phenyl hydrazine, and this one is known as N-phenyl. Okay, this is called as what? 2,4 DNP, 2,4-DNP. Okay, 2,4-dinitrophenyl hydrazine. Okay, this is called as semi-carbazide. Now, so these are the ammonia derivatives. Now we are going to discuss the reactions of aldehydes, ketones with all these compounds. Okay, now in this case, this part, okay, I will consider like this. G is nothing but this one. Okay. Now, so aldehydes or ketones, C double bond, okay, H, it may be R or H. Okay, we will take otherwise we will take out aldehydes R, C double bond O, H, and when it react with H2NG, in this case you have to remove water from this. Okay, so when water is removed, here you will get RCH double bond NG. Okay, so this reaction is called as what? Nucleophilic addition and elimination reactions. So here elimination of water takes place, H2O. If you take ketones, or in this case also H2N, and here it is what? G. I said in this case G is not R, NH2, NH2, PHNH, and this one. Okay, so in this again you remove water. Here you will get minus H2O, you will get R, C, R double bond NG. Okay, now next, so when come to this, when come to semi-carbazide, this is very important. In this we have to remove hydrogens from this NH2 group, not from this NH2. Why? Because here there is a, because of resonance, this hydrogen can't be removed very easily. So therefore, when aldehydes or ketones react with semi-carbazide, we will get this product, R, CH double bond, okay, N, NH, C double bond O, NH2. And when come to 2,4-DNP, this 2,4-dinitrophenyl hydrazine can be used to identify carbonyl compounds from other compounds. Why? Because carbonyl compounds, aldehydes and ketones, when they react with 2,4-DNP, they gives orange or yellow or red color. So with the help of this 2,4-DNP reagent, we can identify carbonyl compounds from other organic compounds. So it can be used for the identification or test for carbonyl compounds, aldehydes and ketones. You know that reduction is nothing but addition of hydrogen. Aldehydes and ketones, first we will take aldehydes, R, C double bond O, H. Aldehydes and reduction in the presence of reducing agents. The reducing agents which can be used in this reaction may be lithium aluminum hydride, sodium borohydride, or nickel platinum palladium. Okay, so in this case it becomes primary alcohols, or CH2OH, primary alcohols. It means aldehydes on reduction, okay, using lithium aluminum hydride or sodium borohydride or nickel platinum palladium, you will get primary alcohols. Now we will take a example CH3CHO, acetaldehyde. Acetaldehyde on reduction in the presence of these reducing agents, you will get CH3CH2OH. This is known as ethyl alcohol, and this is acetaldehyde. Okay. So, therefore, with the help of this reduction process, we can prepare primary alcohols. Now, if we take ketones or C double bond O, or this on reduction in the presence of these reducing agents, here you will get RCHOH, and this is R. You will get secondary alcohols. So, aldehydes on reduction, you will get primary alcohols, whereas ketones on reduction using lithium aluminum hydride or sodium borohydride, nickel platinum palladium, you will get a secondary alcohol. Now, here I am taking acetone, CH3 C double bond O CH3. This on reduction in the presence of say nickel or platinum or palladium, here what you will get? You will get CH3 CHOH CH3. This is known as isopropyl alcohol, which is a secondary alcohol. Why? Because OH group is attached to the secondary carbon, secondary alcohols. Okay. Now, you can take other examples also. CH3 CH2 C double bond O CH3. This on reduction, what you will get? Very simple. So, here this C double bond O group is there, no, that you have to convert into alcohol. So, you will get CH3 CH2 CHOH, and this is CH3. And this is known as what? 2-butanol. Okay. Now, this is about reduction, and we will go for very important reductions. Clemmensen reduction and 𝗪𝗓-Kirchner reduction, very important. We will go for that. Clemmensen reduction, very important. And the reagent used in this reduction is zinc Hg plus concentrated HCl. This is called what? Clemmensen reducing agent. So, in this reduction, carbonyl compounds will be reduced to alkanes having same number of carbons. If you take aldehyde RCHO, this on reduction in the presence of the reagent, you will get RCH3. So, you will get alkane. So, aldehydes on reduction with zinc Hg concentrated HCl, you will get alkane. We will take acetaldehyde CH3 CHO, this on reduction, okay, using a Clemmensen reagent, you will get CH3 CH3. So, ethane you will get. It means in Clemmensen reduction, the CHO group is changing to CH3 group. Okay. Now, if you take ketones or C double bond O or this on reduction in the presence of same zinc Hg HCl, okay, you will get RCH2 R, alkane, having same number of carbon atoms. For example, you take acetone CH3 C double bond O CH3. Here this on reduction, you will get CH3 CH2 CH3 propane. Okay. In this reduction, the number of carbons present in the alkane is same as the number of carbon present in aldehydes and ketones. Now, we will go for one more very important, that is 𝗪𝗓-Kirchner reduction. In this also aldehyde, carbonyl compounds are converted into alkanes having same number of carbon atoms, but the difference is in this case we have used a zinc Hg concentrated HCl, but whereas in 𝗪𝗓-Kirchner reduction we will use a different reagents. They are hydrogen, first step hydrogen, and the second one is ethylene glycol in the presence of KOH or NaOH. So here aldehyde or C double bond OH, aldehyde and reduction. Okay, first one is hydrogen N2H4 and the second one is ethylene glycol, the presence of KOH or NaOH. Then you will get alkane having same number of carbons, so you will get RCH3, and the useful byproduct produced in this reaction is nitrogen. Okay, so therefore aldehydes are ketones on Clemmensen reduction or 𝗪𝗔𝗃 reduction, you will get alkanes. These two are very important, and you have to remember the reagents used in Clemmensen reduction and as well as in 𝗪𝗃 reduction. Now we will go for oxidation of aldehydes and ketones. Okay, the next one is oxidation. You know aldehydes RCHO. Aldehydes can undergo oxidation in the presence of strong oxidizing agent or weak oxidizing agent. They can undergo oxidation in the presence of strong oxidizing agent or weak oxidizing agent and produces carboxylic acids. Same number of carbon, same number of carbon atoms. Okay. Now aldehydes on oxidation, they can undergo oxidation in the presence of strong oxidizing agent and as well as weak oxidizing agent and forms carboxylic acids having same number of carbon atoms. We will take acetaldehyde CH3CHO. This on oxidation in the presence of K2Cr2O7H plus. Okay, here you will get CH3COOH, acetic acid. Okay, here the number of carbons in this carboxylic acid will be same as the number of carbons in the aldehyde. Okay, now and I said they can also undergo oxidation with weak oxidizing agents. So these are weak oxidizing agents. So aldehydes can undergo oxidation with a strong oxidizing agent and as well as weak oxidizing agents. Why? Because you know that among aldehydes and ketones, aldehydes are more reactive. Because of more reactivity, they can undergo oxidation with strong oxidizing agent and as well as weak oxidizing agents such as Tollens reagent, Fehling's reagent and Schipp's reagent. Okay. Now when come to the ketones, ketones can undergo oxidation only with a strong oxidizing agent. Weak oxidizing agents, they do not undergo oxidation with a weak oxidizing agent. They can undergo oxidation only with a strong oxidizing agent such as K2Cr2O7H plus or KMnO4H plus. And when they undergo oxidation with a strong oxidizing agent, then you will get carboxylic acids having less number of carbon atoms. Okay, so here we are getting carboxylic acid and here also we are getting carboxylic acid, but when ketones are used we are getting carboxylic acids having less number of hydrogens, but here we are getting carboxylic acids having same number of carbons. This is very important, and ketones do not undergo oxidation with a weak oxidizing agent because they are less reactive than aldehydes. Okay, now ketoenol tautomerism. So this ketoenol tautomerism can be exhibited by a aldehyde or a ketone which contain at least one alpha hydrogen. Okay. Now for example, say here the condition to exhibit ketoenol tautomerism is the compound, the aldehyde or ketone must contain at least one alpha hydrogen. If you take a formaldehyde, you know that formaldehyde is not having a alpha hydrogen, alpha carbon, alpha hydrogen are absent in a formaldehyde. So therefore formaldehyde do not exhibit a ketoenol tautomerism. The next aldehyde is CH3CHO, and here this carbon is called as alpha carbon and it is having 3 alpha hydrogens. But what I said, to exhibit ketoenol tautomerism, the carbonyl compound, the aldehyde or ketone must contain at least one alpha hydrogen. Here it is having 3 alpha hydrogens, no problem. So alpha hydrogens are there in this compound, so it exhibits a tautomerism. I am writing the tautomers of acetaldehyde, CH2H, C double bond OH. Okay, in this case when these pi bonded electrons are taken by the oxygen and here these electrons will be shifted like this, and this hydrogen will be taken by the oxygen. So you will get CH2 double bond C, and this is OH, and this is H, and this is called as keto form, and this is called as enol form, because it is having a ene and ol, enol form. Okay, and this phenomenon is called as keto-enol tautomerism. So acetaldehyde exhibit a keto-enol tautomerism, but formaldehyde do not exhibit a keto-enol tautomerism. Now we will take one more example, benzaldehyde. Okay, is it exhibit a keto-enol tautomerism? No. Why? Because here it is having alpha carbon. Alpha carbon is there, but it has no alpha hydrogen. Due to absence of alpha hydrogen in benzaldehyde, benzaldehyde do not exhibit keto-enol tautomerism. Okay, so I mean to say that this alpha hydrogen will have some acidic nature. Due to presence of this acidic nature, okay, carbonyl compounds undergo some special reactions like aldol condensation, cross aldol condensation. Okay, now we will go for ketones. Now, the first member of ketone is acetone, that you know very well, and it is having alpha hydrogens. Okay, total 6 alpha hydrogens are there. Okay, so therefore it can exhibit a tautomerism. I am writing that CH2 C double bond O CH3, and it is H like this. Same. Okay, so you will get CH2 double bond C OH, and this is CH3, and this is called as enol form, and this is keto form. And when come to acetophenone, C double bond O CH3, you know acetophenone can exhibit a keto-enol tautomerism. Here alpha hydrogens are not there, but here this is also alpha hydrogen. So due to presence of this alpha hydrogen, acetophenone can exhibit a keto-enol tautomerism. And here, due to, just now I said, due to presence of this alpha hydrogen or acidic hydrogen, they undergo, aldehydes or ketones undergo a special reactions called as aldol reactions or aldol condensation reactions. This is very important. Aldol condensation means the aldehydes or ketones which contain at least one alpha hydrogen undergo self condensation in the presence of a base and forms a addition product called aldol or ketol, and this process is called as what? Aldol condensation. So to undergo aldol condensation by an aldehyde or ketone, the condition is the aldehyde or ketone must contain at least one alpha hydrogen. Okay, so the aldehydes or ketones which contain at least one alpha hydrogen undergo self condensation and forms addition product called aldol or ketol, which on further heating produces alpha beta unsaturated, okay, aldehydes or ketones. This process or this reaction is called as aldol condensation. Now we will take one example, CH3 CHO, acetaldehyde. When acetaldehyde undergo aldol condensation in the presence of dilute NaOH, okay, here you will get CH3 CH OH CH2 CHO. Okay, you will get alpha and beta. Okay, this is called as what? 1, 2, 3, 4, 3 hydroxy butanol, 3 hydroxy butanol, or else you can say beta hydroxy, okay, butanoldehyde, and this is called as aldol. Okay, beta hydroxy butanoldehyde. This beta hydroxy butanol on heating, it loses water. Okay, so you have to remove OH from this beta carbon, and I said this alpha hydrogen will have a acidic nature. Remove one hydrogen from this, so therefore minus H2O, you will get CH3 CH double bond CH CHO, and this is called what? Okay, 2-butanol. Alpha beta unsaturated aldehyde we got here. Okay, so aldehyde, I mean this acetaldehyde react with dilute NaOH and forms a beta hydroxy butanoldehyde, which on further heating produces 2-butanol, and this reaction is called as aldol condensation. And now here the very important how to write the product. Okay, whenever a aldehyde having alpha hydrogen is given, how to write this product, this is very important. Now in order to understand it, I am writing in a different way. This is not the exact mechanism, but okay, with the help of this we can easily write the structure of a product. Now CH3, one acetaldehyde molecule I am writing like this, and in another 2 molecules are involved. Okay, one I have written like this, and another I am considering a alpha hydrogen, CHO. Very simple. So in this case, then what happens? You know that electrons will be taken, pi electrons are taken by oxygen. When pi electrons are taken by oxygen, oxygen gets a negative charge, and you leave. Okay, you have to leave this, you have to remove this as H plus, and that H plus should be added to the oxygen, and here it gets a negative charge, and this CH2 group should be added to the carbon. So here what you will get? CH3. Now you see, this is CH and it is OH, and the leftover is CH2 CHO. So CH2 CHO. Very simple. Now we will take one more example so that you can understand it very well. Say I have taken CH3 CH2 CHO. If this propanaldehyde undergo aldol condensation, then okay, which product you will get? How to write the product in this case? Very simple. I said, okay, one molecule you consider like this, CH3 CH2 C double bond O. Okay, now here I said in another molecule you have to take a alpha hydrogen. So therefore you add that alpha hydrogen to this oxygen, OH, and here it is CH, and we have removed a hydrogen from this carbon. So the leftover will be CH, CH3, and this is CHO. Very simple. Now, and after this you remove water, minus H2O. You will get CH3, CH2, CH double bond, C, CH3, CHO. Okay, very easy to write the products. Now I am taking a ketone having alpha hydrogen, CH3, C double bond O, CH3, acetone. This are now aldol condensation in the presence of barium hydroxide. Here you will get CH3, C, OH, CH3, and this is what? Okay, CH2, C double bond O, CH3. This is called what? Diacetone alcohol. Diacetone alcohol. When it is heated, it loses water. Okay, remove OH from this carbon and one hydrogen from this carbon. So you will get CH3, C, CH3. Okay, a double bond, CH, C double bond O, CH3. This is called a what? Methyl oxide. Okay, so now, and this is called as what? The name, IUPAC name of this compound is, it is 1, 2, 3, 4, 5. Okay, 4 dash hydroxy, 4 dash methyl, okay, 2 dash pentanone is the IUPAC name of this diacetone alcohol. Now, so this is called as aldol condensation. Okay, cross aldol condensation is nothing but the aldol condensation between two different aldehydes or ketones, or aldehydes or ketone is called as what? Cross aldol condensation. So in this case, if you take CH3 CHO plus CH3 CH2 CHO. So I have taken acetaldehyde and propanaldehyde. These two are different aldehydes. If these two undergo aldol condensation in the presence of dilute NaOH, then there is a possibility of getting 4 products in this case. Okay, the aldol condensation between different aldehydes containing alpha hydrogen will get 4 products. How to write these 4 products when the reactants are given like this? In this case, just now we have discussed, if acetaldehyde undergo aldol condensation, okay, we will get a self condensation product, that is CH3, CH, OH, CH2, CHO, and when it is heated, it loses water and you will get CH3, CH double bond CH CHO. Okay. Now this is called a self condensation product. One product we have completed. Now we will go for a next self condensation product of propanaldehyde. So self condensation product is CH3 CH2 CHOH, and this is CH3 CHO, and when it loses water you will get CH3 CH2 CH double bond C CH3 and CHO will get. So out of four products we will get 2 self condensation products and 2 crossed products. Now we will go for the crossed products. These are the self condensation products. Now I am going to write crossed products of CH3 CHO and CH3 CH2 CHO, and in this case first one is CH3 CHOH, and in this I am considering alpha hydrogen. So you will get CH CH3 CHO, and when it is heated it loses water. Okay, and here you will get CH3 CH double bond C CH3 CHO. So this is a crossed product, and these two are what? Self condensation product, and this is a crossed product. Okay, in the formation of this product I have considered alpha hydrogen of this aldehyde, propanaldehyde. Okay, now one more product out of 4 we have written 3. Now the fourth one is, all right, here. Now in this case you have to consider the alpha hydrogen of acetaldehyde. So you will get CH3 CH2 CHOH. Now alpha hydrogen of this, so CH2 CHO, and okay, when it is heated it loses water, and finally you will get CH3 CH2 CH double bond CH CHO. Okay, so therefore whenever acetaldehyde and propanaldehyde undergo crossed aldol condensation, they give a total 4 products. Okay, now among that 4 products 2 are self condensation products and 2 are what? Crossed products. �-��-��𝗧 reaction. What is �-��-��𝗧 reaction? You know, this �-��-��𝗧 reaction is given only by aldehydes which do not contain alpha hydrogen. So the aldehydes which do not contain alpha hydrogen on reaction with concentrated NaOH produces a mixture of alcohol and sodium salt of carboxylic acid. This reaction is called as �-��-��𝗧 reaction. So the conditions for this reaction is the aldehyde which do not contain alpha hydrogen. It should not contain any alpha hydrogen. So therefore the aldehydes which do not contain alpha hydrogen on reaction with sodium hydroxide, they give mixture of alcohol and sodium salt of carboxylic acid. Okay. Now we will take a formaldehyde. You know, formaldehyde is not having a alpha hydrogen. So therefore formaldehyde can undergo �-��-��𝗧 reaction. So formaldehyde on reaction with concentrated NaOH, or else we can write 50% NaOH. Here you will get 2 moles of formaldehyde. Okay, here you will get I said you will get a mixture of alcohol and sodium salt of carboxylic acid having same number of carbons. So therefore here you will get CH3OH plus CH3 plus HCOO-Na. Okay, you will get a mixture of methyl alcohol and sodium formate having same number of carbons. Okay, so in this this is a oxidation product and this is a reduction product. So in �-��-��𝗧 reaction, okay, the reactant will undergo both oxidation and reduction. So therefore this we can call as a disproportionation reaction. You know that disproportionation reaction is nothing but the reactions in which only one substance undergo both oxidation and reduction. Okay, so therefore formaldehyde on reaction with sodium hydroxide, concentrated sodium hydroxide, it gives mixture of methyl alcohol and sodium formate. Okay, similarly we will take one more example, benzaldehyde. and you know that benzoyl are not having any alpha hydrogen, so it can undergo 𝗂-JIO reaction. So when it is heated with 50% NaOH, here you will get 2 moles, you will get a mixture of benzyl alcohol and sodium benzoate. Okay. So therefore, this 𝗂-JIO reaction will be given only by the aldehydes which do not contain alpha hydrogens. Okay. The condition is the aldehyde should not contain alpha hydrogen, and in this reaction we are getting mixture of alcohol and sodium salt of carboxylic acid having same number of carbon atoms. When come to iodoform reaction, this iodoform reaction will be given only by the aldehydes or ketones which contain 3 alpha hydrogens. So when aldehyde or ketone which contain 3 alpha hydrogens are heated with iodine and NaOH, mixture of iodine and NaOH, here you will get a CHI3. This is a yellow PPT called as iodoform. Okay. So iodoform reaction will be given only by the aldehydes or ketones which contain 3 alpha hydrogens, and you know that this iodoform reaction can also be given by the alcohol, which contain 3 beta hydrogens. For example, CH3, CH2, OH. Ethyl alcohol can give a iodoform test because here it is having a this is alpha and this is beta. It is having 3 beta hydrogens. So therefore, it can give iodoform test. Okay. Now, clear? Is it clear to you? So iodoform reaction will be iodoform test will be given by the aldehyde or ketone which contain 3 alpha hydrogens, and this reaction, this test can also be given by the alcohol having a 3 beta hydrogens. Example is ethyl alcohol. When come to the test for aldehydes, aldehydes can give a tolerance test. This is called our silver mirror test. Okay. Tolerance reagent is nothing but ammonical silver nitrate. So ammonical silver nitrate is called as tolerance reagent. Aldehydes RCHO. Aldehydes react with a tolerance reagent and gives a silver mirror. So with the help of this tolerance reagent, we can identify aldehydes. Okay, aldehydes will give this tolerance test or silver mirror test, and they can also give a failing test. Okay, here failing solution A and failing solution B. Failing solution A is nothing but aqueous CaSO4, and failing solution B is nothing but sodium, potassium tartrate. Okay, so this mixture failing solution A and solution B is called as failing solution, and here aldehydes react with a failing reagent and gives a red precipitate. And this failing test is not given by aromatic aldehydes. For example, benzaldehyde, it won't give a failings test. Okay, and aldehydes can also give a Benedict test and 𝗪𝗓𝗪𝗓 test. So tolerance test, failings test, Benedict test and 𝗪𝗓𝗪𝗓 test will be given only by aldehydes, and these tests are not given by ketones. So therefore, by using these reagents we can distinguish, we can identify aldehydes from ketones.